Hi, welcome to my talk. I'm Madhav and I will be presenting our work Poseidon, a safe and scalable persistent memory allocator. With the introduction of NVM, we are entering a new era of memory hierarchy. It is commercialized by Intel and is available in the market as Optane DC persistent memory. This exciting new memory technology provides a lot of benefits and it is fundamentally changing the way we handle and compute the data. These are some of the interesting features of NVM. The read and write latency is on the order of DRAM, and like the DRAM, NVM sits right on the CPU memory bus and it is byte addressable. So the programmers are now able to use load and store instructions to access non-volatile memory. Also, like the traditional block storage devices, NVM is non-volatile. In a nutshell, this new memory technology provides DRAM-like performance with block storage-like characteristics. One of the popular means to access NVM is using a DAX file system. Here, the NVM region is mapped to the user space, and the users can then read or write directly to this mapped region using common load store interface. But the developers need a mechanism for managing these memory regions effectively. That is where the NVM allocator comes into the picture. There are a lot of good memory allocators designed for the DRAM, but designing an NVM allocator is fundamentally different in many aspects, and this is mainly because NVM is non-volatile, which means unlike the DRAM-based allocators, allocators do not have the luxury of being able to ignore system crashes. If there is a power loss or a system crash, memory may have been in a partially updated state, and NVM allocators should be able to recover and restore these partial states. In a nutshell, apart from scalability and performance, an NVM allocator should ensure crash consistency for all its allocation and deallocation operations and should be able to handle persistent memory leaks across power cycles, and mainly it has to ensure safety for its metadata. Unfortunately, none of the existing allocators satisfy all these critical requirements. For example, both Makalu and PMDK scales poorly in many situations. But importantly, none of these NVM memory allocators ensure safety for their metadata. Ensuring safety for the metadata is very critical because if the metadata is corrupted, then the allocator cannot recover correctly, and in some cases, it can lead to persistent memory leak. All these issues leaves the applications that use these memory allocators in a vulnerable state. This is a simple example where a small programming error can lead to metadata corruption in PMDK. First, as shown in the sample code, we allocate all the memory from the persistent memory heap. Let's say we allocate a total of 10 objects of each 64 bytes. Then we corrupt the allocation size field in the header of one of the pointer written by the PMDK memory allocator. Say the size is actually accidentally set to 1 megabytes, which is much bigger than the originally allocated size. PMDK does not detect this corruption, and when this corrupted pointer is freed, it frees 1 megabyte of memory instead of original 64 bytes of memory. This leads to user data loss and corruption, and most importantly, application is unaware of this behavior. Naturally, this will degrade or destroy an application and maybe the entire system. So far, we have seen that interfacing NVM is non-trivial and there are a lot of room for causing data corruption. It is critical for an allocator to protect its heap metadata, and most importantly, doing so should not introduce any application bottleneck. And most critically, the allocator should also provide a scalable performance. To achieve these goals, we propose Poseidon. This figure shows the overview of the Poseidon architecture. Note that the red blocks represent the persistent metadata of the Poseidon and the green blocks represent the persistent user data. As we can see, in Poseidon, metadata is segregated and stored completely separate from user data. We will discuss in the next few slides why this is in fact critical for ensuring safety. Next, the metadata exists at per CPU level and not as a global entity. This enables the thread running on a CPU to allocate and access the memory locally, which is critical for many core scalability of Poseidon. Finally, we protect the entire metadata region from inappropriate access. We use Intel memory protection keys which is a scalable hardware memory protection technique to ensure this metadata safety. In the next slides, we will discuss each of these components in a detailed manner and also discuss how they help Poseidon to achieve its goals. As shown in the architecture, Poseidon separates its metadata from user data entirely. Using Intel's MPK, we can initialize and map a region of memory to a unique key. Then we can simply modify a per CPU register bit to toggle permissions before updating the map memory. In doing this, we can provide a thread-safe and scalable memory protection. Also, updating register is on the order of 20 clock cycles as it is performed in the user space by using hardware instructions. So switching permission is also a low latency operation and does not hinder the scalability of the Poseidon. Now let us see how Poseidon achieves many score scalability. We accomplish this by using sub-heap local entities. Let's examine this a bit. Note that PMDK creates a giant heap in the socket of the main thread, and now if we let an arbitrary number of threads run, and if a thread on the other socket needs memory from the heap, it will have to read or write across the socket interconnect, which becomes a critical bottleneck. Additionally, it leaves some of the memory controllers unutilized, and which is again a critical bottleneck in NVM systems. With Poseidon, however, the subheap is designed to be initialized on a per CPU or per thread basis. This allows full utilization of memory controllers and enhances locality and does not require crossing the NUMA socket. Due to time constraints, we discussed only the safety and scalability aspect of Poseidon. For more information on Poseidon design and implementation, please refer to our paper. Now we present our evaluation. We first evaluate scalability of Poseidon relative to the other NVM allocators, namely Makalu and PMDK. Finally, we evaluate Poseidon in the real-world applications. For our benchmarks, we use micro benchmarks, high-performance computing benchmarks, and real-world benchmarks to evaluate Poseidon and the other NVM allocators. We run our evaluation on a 2-socket 112-core machine with real NVM, and our machine consists of 3 terabytes of NVM with 6 NVDIMMs on each NUMA socket. This figure shows the performance of different NVM allocators for a micro benchmark which randomly allocates and frees 100 blocks of memory for 1 million iterations. It is important to note that performance of all the allocators are not size agnostic. Particularly, the performance of Makalu plateaus for allocation sizes greater than 400 bytes. This is mainly because of maintaining a global free list design in the Makalu allocator. On the other hand, Poseidon scales almost linearly for all the allocation sizes and thread configurations. In this figure, we demonstrate the performance of NVM allocators for different high-performance computing benchmarks. As shown, Makalu is non-scalable due to its global free list design. And then PMDK fails to scale beyond one NUMA domain, as accessing and allocating memory across NUMA domain saturates PMDK's performance. On the other hand, Poseidon scales linearly and performs up to 9 times faster than PMDK and up to 20 times faster than Makalu across all the benchmarks. There are many more interesting evaluation results in the paper, and please refer to our paper for real-world server benchmark and YCSB evaluations. To conclude my talk, we presented a new persistent memory allocator named Poseidon, which is safe and scalable. Poseidon guarantees safety using Intel memory protection keys, and Poseidon's sub-heap design, per CPU sub-heap design, enables it to scale almost linearly and consistently outperform its competitors while providing additional safety guarantees. Thank you for listening to my talk, and I will be happy to take questions.